No, I didn't say meaningful. The amount of computing power it takes is so enormous. Remember though, at one time, we are not solving just one problem. There are 60 problems, let us say. Should I use all the computing power I have and solve this multi-billion atom of one problem? Or should I be solving 3 different problems with 3 different things and essentially solve a smaller problem? So it's a constrained situation. So I'm not saying if I had infinite computing power, everything I would solve multi-billion, including ab initio, right? But I cannot. I have finite computing power. So I need to be able to balance the total computing power versus what is the biggest value I get out of that simulation.
But Axel Kohlmeier, who is in Penn State, he was claiming that last year about 270 million particles are simulated in IBM Blue Gene machine, which is the at present the most biggest power. Yes, through coarse grain modeling.
Okay, so it's maybe more like a multi-scale.
Yeah, 200 about 70 million particle within a week time in Blue Gene machine.
Yeah. So may I ask again the same question? What kind of information has anybody got out of such simulations?
Yeah, multi-billion.
Yeah. What would you look into? Suppose even that you have very good potentials, or even ab initio, or even quantum chemistry. Suppose you have a magic black box, the Intel super processor.
So where would I need the billions, right?
Yeah. What would you learn from? What would you look into?
Excellent. I will give you 2 examples. In one, we would like to know the transition temperature of a polymer, glass transition temperature. In order to predict glass transition temperature, we don't have simple linear polymers. They're very complex structured polymers. And most of the time, the glass transition temperature that's measured outside seems very different when it is put in conjunction with 2 different materials. So if I were to have, let us say, excellent potential, I would go in and simulate that whole structure in which the polymer stays, which is of the order of 100 nanometers, with interfaces, different interfaces. And I would try to predict the glass transition temperature of that polymer structure. That's one. The other example is, if you were to look in 15 nanometer or even 22 nanometer technology, we put incredibly transition and inner transition metals, gates and dielectrics and all that. We are looking for mobility, prediction of mobility. The prediction, people have found experimentally and theoretically using some analytical work, that there is something called remote phonon scattering. Things 20 to 30 nanometers away affect the channel mobility. But in order to be able to simulate the whole channel, the source, the drain, the dielectric, which is 3-layer or 4-layer, and the gate, quickly brings me to the order of 1 million atoms. So if I could do the ab initio, then I can conceivably look into those chromometers. Right now they are done by semi-classical Boltzmann. You have a hierarchy of methods you use, like a coarse grain technique to get that. If I had choice, I would go with full ab initio. It's all the problem. Because then I know that I am much closer to reality. And that would be of the order of 1 million atoms, the structure that it has.
But still, I think that new ideas will continue to be important. I mean, if you rush into the multi-billion, then you will have a multi-billion. So, in order to simulate the influence of the moon on the Earth, you don't have to simulate every atom on the moon and every atom on the Earth. So, at some point, I think there must be a way. So, this multi-scale business,
I didn't touch on multi-scale at all. Because I am neutral about it too.
It's important. So people call multiscale anything at this time. So these are I'm very critical about this. But this is sociology. But I think the idea of multiscale is an important one. So is the fact of being able to look at important aspects of processes and phenomena that occur at different landscapes.
Mm-hmm.
So it's the example of the moon and of the earth. This is a typical multi-scale problem. I mean, at the scale of hundreds of thousands of kilometers, that scale at some point is decoupled from the scale of nanometers. And it is important to have tools and methods and ideas to look selectively at different scales with different accuracy.
So the way I put it, I think your points are valid. Blindly rushing into atoms for the sake of atoms. You might as well spend the energy in getting more accurate ways of representing what you know. I mean, I'm not disagreeing with that. However, if I were to have my wish list, the number of atoms is one of them. I'm not saying 10 to the power 23 atoms.
No,
I'm saying with million I will be happy.
No, but
if I look to ab initio on a million atoms, I'm happy.
Humans are greedy, so you don't want to have a 10 to the 23 because now you have 10 to the 3. And you would be happy with 10 to the, what would be your
silicon density is 5 times 10 to the power 22 per cubic centimeter.
Okay.
So maybe that would be my upper limit.
Okay.
Less than the Avogadro number. And so the trick is, I think Stefano's points are well taken. It's not the size for, which is why it was one of the list of items I had, but not the top one. I had more of the physics-centric things first, because that is where we are spending a lot more energy. But constantly, the limitation of number of atoms come in, and that was the only point I was trying to.
Of course, you want not to be limited by the number of
That's
atoms.
right. That's right.
This is important, not to be limited. This doesn't imply that just the number of atoms would
solve it. No, that's why I had 13 other items, which had nothing to do with the number.
Other questions? Comments? What would you recommend? You have an audience of young, bright brains, and suppose you have a problem for each of them, or for a few groups of them. What would you recommend for a bright career in materials modeling?
I think that the area of nano...
Give us 2-3 problems, not general problems. So we understand the lecture was very illuminating on general fields. But give us 2-3 challenging problems that could be solved in 1 to 3 years. These people can start their career with by solving one of your 2-3 problems.
So I will start from 3 to 5 years first.
Okay.
Almost every problem you are going to see in energy, in biology, and even in semiconductors are non-equilibrium systems. So they are essentially open systems. My intent of that is, if there is one area to concentrate, it's your ability to simulate open non-equilibrium systems of structures, not bulk materials. So I want structures which have multiple interfaces and ability to simulate it, even if it is DFT or GW, that's fine. But the ability to be simulating the entire process of non-equilibrium. The reason I'm saying non-equilibrium is that is the single source of a lot of interest in physics and chemistry. in almost 3 major industries. I have gone and looked at it in enormous detail. If you pick up biology, energy, and nanotechnology, all 3 of them have this in common. So that I would put it 3 to 5 years. The second thing, which I would put it maybe 1 to 3 years, would be interfaces. Interfaces have a lot of problems. I kind of went over that quickly. The problems with interfaces is you need to have you have mechanical strain. You need to be able to bring multiple interfaces together. You also need to be able to have interface states very well accounted for in ab initio models. So that's an immediate problem. If people can work on putting together complex interfaces and be able to minimize the energetics that you could use. Generally, we don't have nice silicon sitting on nice germanium. That's not the way it works. Silicon substrate, what we call silicon, or anybody calls silicon, has 5 different atoms in it. So it's not just silicon. You need to be able to have a nano thin film which has multiple elements in it, sitting on top of another nano thin film which has multiple elements on it. The ability to simulate the interface density of states, transport across interfaces, and properties at interfaces would be the 2 most important things I could think of. There are others which are connected because they're not distinct. You cannot do the transport part if you don't have the other ones. You pick up any problem, I can show you examples of why these 2 would be important. Any industry, any fundamental problem. So those would be the 2 I can think of. Do you see that my rationale? I hope I tried to set it up so that you kind of see these problems as critical.
So if anybody solves one of these problems, it will get a very good operating intelligence.
Quite possibly. Quite possibly, except it's not up to me. Right now we have a hiring freeze. But if the hiring freeze releases up and somebody shows, I can even set up the problem. Actually, I can go back and give you more distinctly defined problem to the quantum espresso community.
Great.
Let's see you solve that problem. We will really take it as a good challenge.
We take you seriously. Okay.
I was being serious. It will take me some time, but we could set up 2
Great.
or 3 problems.
Yeah, we are patient. Any other questions? If not, I have a very last one.
Sure.
Very last, and maybe somebody else will come out with another one. From the point of view of software, so these 3 problems that you mentioned were from the point of view of materials, materials and physical and chemical sciences. Your wish list as far as simulation software is concerned, what should this community do for you?
That's a good question. I really am kind of excited by where quantum espresso is going. We are trying to help out a lot of other components as well. If you ask me 2 things, the ability to simulate electronic properties as functions of externally imposed field or force is a very difficult problem. You could ask me, why is it a software problem? It is a software problem because the kind of codes which are accurate in electronic structure are not the codes which can do this external field. So there's a gap. The capability exists.
Give us a definite example so that we make sure to understand what you mean.
So I'll give you an example of a CNT. I gave an example of metallic CNT, and Louis talked about semiconductor CNT. In both of our graphene, in any of them, you essentially impose the electric field. If you look at those strain transistors, there's a mechanical field, which is stress, and an electric field. I would like to be able to simulate density of states as a function of these two fields. That would be a software thing, because the issue is more of practical implementations. It's not physics, it's practical. The second thing, from a software perspective, is I would like to have, if I'm using any DFT code, would like to have pseudo potentials for the 70 elements I showed. This one I'm really serious about. I can even get money for this. Nicola knows this. I'm talking to Nicola about it. So the second one is a very critical factor. That's again a software thing. That would be, I would leave it at that. There are more, but I don't want to just flood you with information, just give you indications. That would be.
Other remarks?
Any other comments, suggestions?
If not, we thank you again. And we reconvene tomorrow morning for another half an hour.